Let's wait for another 5 minutes and then we'll start. Has everyone watched Avengers Endgame?
I'm here coming for the first time.
No, Avengers Endgame I'm talking about.
No. He's asking about the movie. Avengers, yeah. I didn't get a chance to go.
Okay.
By the way, how is it?
It's pretty cool. If you want spoilers, I can reveal
No,
things.
I don't want spoilers, but people will become very angry after seeing the movie.
Yeah, because Iron Man dies.
No.
More spoilers coming if you want it.
So here's the point that we can like introduce ourselves. Like, I do not know anybody.
Okay, so I'm Yash. He's Utkarsh, and another guy who's coming. His name is Aman. So we three have formed this meetup group, and we are looking out for any contribution from your side as well. So if you want, you can easily join us and present whatever you know have worked on some interesting problem or something. You can present that.
So you are working in the same PI.
Yeah. We all three are.
On the video.
Yeah. Aman, by the way, is a student, but he's doing some internship.
Okay. So you are already working.
Yeah. How about you guys?
My name is Viraj, and I am currently working with the Mercedes.
Okay.
And my work involves some part of risk analytics. And I'm more interested in learning this.
Okay, nice.
As far as concepts are concerned, maybe a few I know, but as far as hands-on is concerned, I will get more.
Okay.
My name is Sharon.
Okay.
We'll have a calling system that equals to this very fancy things.
Okay. Last week I was this week I'm okay, sure.
And And then, sort of machine learning I was doing is it was it is like they have programmers integrate. Apart from your data, you can do whatever with your own model, and you can spend 20% of your time in that. So I was doing NLP and things like that. And then now new organization and coming into VM and cloud things like that. But in part of other department, I doing analytics or the data. So I don't have, I'm not part of that team. Right? But my main interest is in machine learning, deep learning. I've been like studying it, taking online courses, learning, but I'm still not completely, I don't have full knowledge on how it functions. I want to get more into it, like, give.
Myself, Sudeep, I'm attending the session from past 2 weeks. I have attended this place to trial from there. So I work in deep learning, but mostly with exceedance it's startup kind of stuff. So I work with some startup algorithms like SSD. Now currently I'm working for some basic intelligence system. Building my basic intelligence.
Sure. Okay, so I'll begin. Utkarsh, yeah. So let's start. So, so Joseph Redmond was a guy who invented Yolo V2, Yolo V2, Yolo V3. So he's the man behind it. So this all started with this CVPR conference where SSD guys and the YOLO guys were competing each other, and they were like they were eventually against accuracy, performance, and then YOLO V1. So SSD beated YOLO V1, and then YOLO V2 emerged when they wanted to beat SSD. So that's how is the story. So uh, so, okay, let's give you a basic introduction of how it works. So, consider you're shifting a place. Okay, let's say you're situated, let's say in Whitefield, and you're moving to HSR. Okay, so you need to do packaging, right? So different objects needs different bounding boxes, right? So I mean different boxes, like say for packaging, right? So now you go to market, you want to buy some cardboards. So you can't buy single a custom cardboard for every object you have in the house, right? So what YOLO guys do is they take all the bounding boxes from the Coco or Pascal or whichever data set they want to train on, right? And then they do a k-means on that. Yeah. So yeah. So here is the performance you can see. Since this is a single shot detector, so they are just showing over the two shot detectors, right? So see, everyone knows, right? What's a single shot? What is a yeah. So this gives a good performance.
Single shot detector in the sense it doesn't keep convolving over the entire image.
No, it means that you are going to pass the image once. Like you are going to go through the image just once, not twice. That is the case in faster RCNN or fast RCNN or RCNN. Okay, so single shot is like you pass through the entire image once, and then there are multi-shot detectors, right? Who do some region proposals and then do a classification over there. So it's like you are passing it twice, right? So okay, so this what happened in CVPR 2016. So they were trying. So this is basically the Redmond guy. Okay, so he's trying to he actually was trying to detect. So here it was saying exit. Okay, but then over here it used to say toilet. You see the toilet thing, but it's not actually a toilet. It's a group. So this was the downfall of Yolo at the first time when they released. So then there was a new iteration in CDPR's 2017, wherein they actually beat SSB. So yeah, work it harder, make it better, do it faster, makes us stronger. So this was the motto. This is the actual thing which is written in the paper. Okay. So it's actually the YOLO architecture emerged between the rivalry between those two. So how the training phase started, like they train for classification on ImageNet, okay, and then they did fine tuning on detection. Okay, so because I didn't broadcast.
Yeah, I started from.
You started.
Yeah. Yeah.
Camera?
What was it?
Okay. So, so how they came up with the basic amount of anchor boxes which could cover all the objects, right? So as I told, so if you are moving from wide field to HSR, you cannot take so many bounding boxes to move each and every object, right? So what they did was they did some kind of a clustering to match all the objects, okay, but then to get the but to take a minimum bounding boxes. Okay, so this is the approach. So using k-means, what they did was, let's say these are the number of clusters. So every cluster means, like, let's say there is only one bounding box. Here they are using two bounding boxes. Okay, so basically they arrive at after doing k-means for all these values, right? They arrived at 5 being the most appropriate considering the accuracy they are getting, the average IOU. Is everyone familiar with what is IOU is? Intersection over union, right? So to get an optimum IOU, they found out that 5 is the minimum. So if they can actually go 6 and increase the IOU, but then it will again play around with the performance. So to just get an optimum, they took 5. Right. So these are the 5 anchor boxes which you can see over here, and these are these are the all the, let's say, from all the images which they got, and these are the actual ones which they have found out. So these are, you can say, the centroids of the each of the k-mean cluster. So yeah, so here you can see what's the average IOU they are getting from 5 clusters. I mean 5 anchor boxes. And if they go to 9, it just increases a bit more. There's not much of an increment, you can say. Okay, so yeah, so and in YOLO V2, what they did was they trained for multi-scale, objects. Let's say this is your actual object, they just scale it up and scale further. So that so even if the object is small, let's say if you have trained it for small objects, and suddenly if the object goes big, when the camera is taking a shot of at it, you can detect that object as well.
Yes, right now.
Yeah.
Is resizing and rescaling both same or different?
Resizing and rescaling. Scale, when you say rescaling, right, it's based on the one scalar object. It's one. You're scaling it by one. You're scaling it by two. Resizing, you play around with the aspect ratio. So it's like you are changing the width and the height, you can say.
Okay. So in good scenario, the image quality will be less. Matlab, whether there will be any change in
Yeah, so resizing would change the dimensions of height and width also, right? Suppose there's the object, now I can resize it to be a rectangle, so the dog can kind of expands a bit vertically like that, right? So a bit of the meaning eludes when you do a resizing in such a, but then if you do a rescale, that means you're increasing the height as well as the width in the same way.
the same.
Yeah, like by a factor, by the same factor.
So there won't be any loss in the of information in the by rescaling.
Yeah. So this is the Yolo architecture. You can see where it lies currently and how about others. Like SSD is over here in terms of performance, and Yolo is over here in terms of performance, right? And V3 comes a bit here. Like it's more about accuracy than performance. So V3 is a bit lagging somewhere. So it's somewhat over here. You can say near SSD 300. And you can see again how much of MAP you're getting. So based on different classification architectures. So you can see this is like a performance graph and this is the MAP graph. So you can see like over ResNet you are getting a little good performance compared to Inception, Bindnet, and others. But then if you consider VGG architecture, you'll see the performance is improved. Okay. You'll get a good performance over classification. But then if you consider Inception, the performance goes like ResNet architecture, you see the performance goes for a toss. But then you get a good accuracy. And yeah, so this is kind of real time. If you want to get a real time detection, this is the thing you have to pay. So when you say this is almost near real time. That's why you say that this is near real time. So you can see the green dot. So the green one is basically the ResNet 101. So that was the aim basically, to improve on the performance than the this thing. So you can see Yolo V1 is over here and yeah, so the ResNet 50 gives around 90 FPS and then VGG 16 gives around 100. So you can always go for the 181, which is actually this one, ResNet 101. And yeah, they came up with a new darknet architecture, right? That is implemented in Yolo V2. So that's like a custom classifier for you can say for the V2 method. And, yeah. So you can run it anywhere since you don't have to use much of the hardware. You can run it on the phone or a camera. Anything. So yeah. So when you talk about Coco, there is 100K images and then 80 classes and it has all detection as well as it has a segmentation label, so you can do anything with it. And ImageNet is again the same, but then you just have a label. It's not about detection. So you can. So the way training that was done was that For classifying, we used ImageNet, and for localizing, we used Coco or Pascal VOC or something like that. So it's kind of transfer learning, you can say, for the classification. We can just download VGG16, or let's say a pre-classified, like classifier which is trained on classification, and then you can train on Yolo for localizing and detecting the bounding boxes. Okay, so these are the classes of Coco and ImageNet. You can have a look. And, this is something which is combined. So we are combining both of them together for classifying. It's always better to have more data in the notebook. So, yeah. So there is the WordNet, which has a structure. So WordNet is something which is combining everything. It has a hierarchy as well. Along with that. And this is the tree of the same data set. Okay. Okay. Yeah. So there are three things. One is the objectness, one is a bounding box, and one is a classification. So these are the three types of class things a YOLO algorithm should do, or any object detection algorithm should do. So objectness states that if I'm saying this is the image, where is my object? So it's something to do with localization. Okay, and the classification, when you say which class it belongs to. Okay, it's an object. Which class does it belong to? Okay, and bounding box talks about if this is an object, if this is of this class, how much of it is in the entire image? Like, where is that? How much is that object covering in the entire image? So this is another example. So if you see, so here every cell is trying to predict that it's a golden eagle, but there is an actual cell which predicts it right. So you have to, so here you have to do some kind of a suppression of the others with respect to this. So this is another thing which you talk about. So yeah, this is there's another thing wherein suppose two objects are closer, right? How can you eliminate? How can you say that this is one object and this is the other object, or this is the same object? So how are you going to play this? So these are the problems, typical problem statements which you have to address while doing some kind of a training or testing or whatever. And the same. So this is quite easy because these are two different objects. So let's go through the paper as well and revise the code. So this is the paper, right? So I'll just show you the meetup page and how you can access the materials and stuff. So here's the paper link, you all can download that. And here are the previous session content. You can also see. Yeah, so here's the phase 2 content, and if I see all of them have just joined in the phase 2, right? So you can access the phase 1 content from here. So here we talked about transfer learning, classification, basic deep learning. So all these things, if you want to access, you can access it over here. And the phase 2 content. So today's session content, I'll be putting it over here. I haven't put yet. So you can access the phase 2 content over here. So we have already put in SSD and faster RCNN. Right. So here's the YOLO paper again. Uh, just wanted to show you this. Yeah. So these are the differences between YOLO V1 and V2. So before this, there wasn't any concept of batch norm when started. Like there wasn't like batch norm was like just at a primary stage. You can think about. So they actually released it in 2015. So people used to just use normal normalization and not batch norm. So, so this is that. So V2 has this, and high risk classification is about training on multi-scale, different scales and all. So that happened in V2. Uh, FCN, so it's a fully convolutional network. And yeah.
It doesn't have any density, it is fully.
Yeah. Okay, and here we talk about the performance and others. So here you can see the training comes in the different phases. So first you have to train for classification, and then for detection, right? And and then for both. So I'll show you. These are basic classes and how it did the problem statement. Sharing this soon, but I'm just having a look at this. So here I'm trying. So here we have trained it for Pascal VO3 dataset. Okay. So you can download. Maybe I'll download and share the link so that you all can also train it hands-on. Good. Push that. Push. पहले कभी क्लिक क्या करिए definitely बस अपलोड करूँगा
Add as a contributor. One person now.
फिर GitHub को
You need to pull. You first pull it. Did you pull this?
this one
Just pull it. You can push this.
ये there.
So go to I send us an email. Three people. Email from.
Yeah, or else push it to my GitHub.
I think follow. Follow.
Yeah. Then
Send us the email.
85.
Show the email. So,
हो जाएगा.
इसमें देखो मोबाइल आएगी. ये ऐड नहीं किया है. तो उसको शेयर करो. ईमेल आईडी.
because एक और ऐड अपने रेपो में डाल देते हो बाद में ये लोग उधर से ईमेल आएगा.
Or you just go through because many people are fraudulent. Nobody pays, just go through the books. Previously share it.
हाँ ठीक है.
Go through the books.
So I'll upload over here one more. You guys can access this from here. If anybody wants to train or something, can use this link. I'll just paste this link in WhatsApp or maybe you can check it out. So if anybody wants to train it, you can do it over here. And take this and do the training if you guys want. Okay. That's all I have. So I'll just go through it. Yeah. So, so this all is a data prep stage, right? So here I'm dividing the train and test. So this is the data prep stage, and I'm creating my data set basically. These you can see are the classes, right? And there are some parameters which, if you want, you can tweak this according to your data, right? So And then this is the sort of bounding boxes which I'm trying to use. There are other ways also to use a bounding boxes. Here we are using X min, X max, Y min, Y max. Okay. You understand, right? What is this? So consider this as the image. Where is the X min and where is the X max and where is the Y min and Y max? If you are considering this as a bounding box. Right. So and this is how the prediction is being done. So here tx, ty are the x and y of that particular grid, right? So here right? So entire object is divided into grids. So imagine this is the object. So this will be one grid. So in Yolo V2, what we do is we divide the entire object into 13 cross 13 grids, right? And then
For that, first we have to identify the object. The first object identification has to be.
Yeah. So no. So I'm talking about how the data preparation and how is the architecture. So when you classify, right? It so every grid cell will do a one single classification. So let's say this is the entire image. So we divide this into 13 cross 13 grids. So let's say this will be the first grid, right? So this grid would say whether this has an object or not.
Oh, object, yes or no? Only that.
Yeah. No, first it will say that, and if it is a yes, then it will talk about the prediction. Every grid cell gives prediction of bounding boxes, classification, objectness. So it's about how you are considering it. So if the objectness is yes, then then we talk about the classification, then we talk about the bounding box. But if the objectiveness is zero, we just don't care about it. Because we know that there's no object, so why do we bother what the class it's saying or what's the bounding box it's saying, right? So tx and ty is actually the basically the grid which we are talking about. Okay, which grid does it come in the x coordinate and the y coordinate? Okay, and t, w, and th are basically the from that particular. Let's say this is a grid. Keeping this as a centroid, what's the width of the entire object? What's the height of the entire object? Okay. And TO is the objectness, right? Objectness. So whether there's an object or not. And here we'll do some kind of encoding of that to get bx, by, bw, bh. So encoding is basically this is kind of an offset, and this is a sigmoid of the prediction. So we're taking the sigmoid of the prediction and taking this as an offset. So let me show you what does that mean. So consider this grid is trying to predict something, saying that this is basically here is the object, okay, and this the blue is the ground truth. So this is basically in the Pascal VOC. So this is how. So someone has actually drawn saying that this is, let's say here there's a dog or a cat, okay, and this is what the Yolo algorithm is predicting, the dotted one, okay, and this is the width of that, and this is the height of that. So this PW, you can say this is the prediction. PW is the bounding box. So this is the actual one. This is the ground truth. Okay, and CX and CY is basically the cell, which cell you're talking about. So whether it's the first one or the second one or the third one, and this becomes the offset. So considering this as a cell, so if this is the cell, right? What is this distance? This is given by sigmoid of ty, and this distance is given by sigmoid of tx, right? And, so these are the various ways to predict the confidence score. Okay, so if you want to find the box confidence score of, let's say, this is the actual box or not, so it's given by probability of it being an object and what's its IOU. with respect to the let's say with respect to this, right? And classification, class probability. So it's like if there's an object, which class does it belong to? So it's a conditional probability saying that if the objectness is 1, what's its probability of being a dog? Something like that. So this is somewhat, suppose the objectness is 0, right? So this is automatically 0, right? And what's the class confidence score? So this and this is a little related, but they're different. So it's like what's the what? So suppose there are two different objects, okay, but then they represent the same class. Okay, so here we use this. Right? What's it being like? What is the? Let's say there will be. Let's say there are two dogs side by side, right? So one bounding box would be to both, and one bounding box would be, let's say, to the first dog, and the second bounding box to the second dog. So their IU will be less. Let's say for the entire, let's say there was a bounding box for the entire both the dogs, the IU would be 50% for that particular for that particular anchor box. But for an individual dog, it would be, let's say 100%, like close to 100. You're trying to understand what I'm trying to say here. Show it to you. Yeah, let's take this as an example. So consider this as your image, right? So the bounding box would be, let's say there are three bounding boxes. One is so there would be three bounding boxes. One, let's say, being this. Okay, one being this, and another being this. Being this. I mean this. One this, one this. Let me draw it out or something. So let's say one bounding box is this. Okay, I mean somewhere like this. And another bounding box is somewhere like this. And another bounding box will be somewhere over here, right? So the ground truth will be for this, right? Let's say this would be one ground truth and one ground truth, right? And this there wouldn't be any ground truth for this, so it would try with the biggest one. So let's say this, okay? So,
But it's one thing, the bounding box which is there for both of them won't be, then the box confidence score will be, there won't be box confidence score further. See, you said here there are three bounding boxes.
okay.
Three bounding boxes, what is box confidence?
No, there will be only two bounding boxes. So let's say three.
What predicted? I'm saying Yolo predicted three bounding boxes.
Yeah, Yolo would predict three anchor boxes.
Yeah, three anchor boxes it predicted. So to calculate box confidence score, I'll calculate the IOU. The IOU is the three bounding boxes, and I'll take the ground truth boxes and then calculate the IOU.
Yeah, so the IOU for this
Yeah.
for this particular anchor box would be close to 1.
This
Anchor box bounding box IOU for this particular bounding box will also be close to 1.
yeah.
But the IOU is what? Intersection of a union, right?
Yes.
So let's say this is the prediction and this is the actual, right? So intersection is this by the union, divided by the union. So union will be this. Okay, so it's like this. Let's say this is 5 divided by 10 will be around 50%. So the IU is less for basically this anchor box, right? So in that way, the conditional classifier. What is that? Yeah. So the class confidence score would be less. Okay, so this is how the scoring matrix is being used. Then, and let's talk about non-max suppression, or maybe before that we'll talk about loss. Okay, so these are the data augmentations which was being used in the Yolo algo. So, so this is one such is crop. You're randomly cropping the image, and also basically you're playing around with the anchor box as well, right? And so here you can see we are adjusting the anchor box over here, and we are cropping it, whether it's left crop, right crop, or bottom crop. Right? How much you're cropping. So that also is randomly, being generated. And here is a vertical flip. So you're just, flipping it vertically. So it's like just opposite of this. Right? And this is you're playing around with the HSVA of the image. Everyone knows, right? What's the HSVA? You're playing around with the saturation and contrast, basically. And here is the resize. So I was talking about the multi-scale thing. So this is the resizing thing which was being used. And this is the loss function basically. Um, so the loss function itself contains 3 kind of losses. So here, don't get scared by this equation. Right? I'll just break it down for you. Uh, so there's a classification loss, localization loss, and a confidence loss. I think by the name, everyone just understands what it is, right? Maybe someone can just give a recap on for the new guy who just joined in. Anyone?
Classification clause is nothing but if I predicted that class in the training data and I'll compare with what actual label is and I'll just compare the difference between those two things. It as a classification clause.
Yeah, basically it's trying to classify between let's say 100 classes, which class it is. If this is an object, what class does it belong? Yeah, and localization loss.
So the classification loss is only going to be a binary. Right?
How will it be binary?
Either the classification loss is 0,
Okay.
otherwise it is 1.
No, so it's yeah, binary as in it won't be binary. It will be between 0 and 1.
So, but we cannot say that. If dog is classified as cat, we cannot say that it is a less difference. Whether dog is classified as a breed. Let us say that there is a dog.
Okay.
Let us say we classified it as a cat.
Yeah.
Next time we classified it as a building. So we
Next time you
classify it as a chair.
Okay, let's say it says classified wrongly.
Yeah, wrongly. Right?
Yeah, so there will be a loss would be close to 1.
So I asked whether is it loss is going to be either 0 where it's classified correctly, or it is going to be 1 where it's classified incorrectly.
No, it won't be exactly 1. It will be close to 1.
Close to. It doesn't matter which.
It's not binary. It's not like binary thing.
Okay.
So it will be a probability.
Okay. So which part of it is telling the classification loss?
Yeah, I'll just show you. So this is the classification loss. So probability also of this being a class. So it's like a square difference.
Okay.
Okay. Square difference. Yeah. And what's the confidence loss? Can anyone just give me what's the confidence loss? So it's basically the bounding box confidence, which I talked about over there. This one. bounding box confidence score. So basically it's that loss. And this comes along with the objectness as well. So this one of objectness you can see, right? So it's like if there's an object, it would be one, otherwise it will be zero.
That is coming from ground.
That is coming. So you're comparing against the ground floor, right? So if the grid cell says its sort of object is there, so that would be
one. Otherwise,
and then comes about the localization loss. So here we are talking about the x, y, and w and h. So suppose this is the grid cell, right? And this is the grid cell which is actually saying that it's there, and this is the grid cell which is saying this is the prediction basically. So we're just doing a difference squared with the x and y to predict that, to get the exact cell we're talking about, and then here this will give me the width and the height of the bounding boxes. Right? If let's say the aspect ratio is too high, right? So it will try to reduce that to a particular height and so on. It picks up one particular anchor box and says that how much you have to rescale it. Okay. So here we are going to make five such predictions. So every grid cell will spit out five predictions with respect to each and every anchor box. So remember we took five anchor boxes, right? Let me take this as an example. So for example, this dog image, right? This particular, let's say this particular cell would be saying there will be five such anchor boxes. One would be something like this, one would be something like this. I mean, so we have to just check which anchor box best fits, right? So there we use confidence score, and for using that as well as this, the x, y, and w and h, right? We are going to predict, compute the loss, right? And I'll show you this is the loss. So you can see, right? This here I've defined MSE and cross entropy, and I'm just this is basically the coordinates, right? The coordinate loss x and sorry, this is the coordinate loss, and then this is the confidence loss, and here is the classification loss, right? And here I'm just summing it up. And when you talk about training, right? So remember I told you that first we are going to train for the classification, and then we are talking about the localization, right? So how we are going to do that is using this lambda chord. So in the entire loss function, you can see there are these parameters called lambda chord. Okay, so here we try to say that what you are going to predict for. So if let's say this is one, we are saying that talk about localization first. Do localization, train on localization. If you are setting this one, please train on classification. Okay, so it's about how you want to do the training.
even when, let us say, we want to first train on classification and then do a localization, we should have two different loss functions.
No, we are using the same loss function. We are just playing around with the parameters. So this lambda chord which you are saying, right? So this lambda this lambda is basically is a scalar thing. Okay, so if it is 0, you're not considering this particular loss, right? So in that way, we are using the same loss to do to train on classification first, and then on localization, and then on both. Try to understand this. So let's say if I put this as 0, right? So whatever is the x and y, or whatever is the w and h predicted by my neural network or FCNN, we are not considering that in the loss function when you are doing a gradient descent. We are just considering this classification loss. So the entire network would learn on classification first, right? And then we are talking about the localization part. So then we will maybe set this to 0, and then we'll set these two things to 1, right? And after setting that to 1, we are going to do the training part, the back propagation part. So we are just passing on this loss. And then we are setting all the three things to 1. Or maybe if you want, you can set it to 2 as well. So you are penalizing more on that classification.
And if it wants to be
So this is how I've just broken down into classification parts, okay, like losses. So these are the 3 losses which you can go through. So this is the Yolo architecture. So, so this is basically the darknet 90 which I was talking about in the Yolo V2 architecture. So you saw that, right? That it was giving us 200 frames per second, right? So this is that. So maybe I'll show you that slide.
This dark is kind of feature extractor.
It's basically the classifier which we are talking about. So the classification part is handled by the darknet 19 network.
Only classification, or it will give me some feature maps also.
Yeah. So at the end of the classification, you get the scores, right? But before that, there are feature maps. So these were used in Yolo V1, right? And they came up with their own classifier which is known as darknet 19, right? So you can see the increase in the performance, right? And also the accuracy. So it's around this, so which is quite fine. So it's like you can see it's giving an accuracy compared to Resident 50, right? And the speed is almost double, twice of that, more than twice. So that's how they have optimized it. So to talk about this architecture, you can see so there is a regular convolution max pool for around let's say 1, 2, 3, 4, 6 times, and then at the 5th convolution, you are just passing a skip connection over here. So you can actually play around where to pass in the skip connection, and along with that pass it through padding. You can play around with that if you want to. But they found that after training that this is the best position to pass in a skip based on the receptive field of the objects you're training on.
One doubt. So there are multiple convolutions in single layer. So whether they are concatenating the result of, I mean, they are doing the stuff in parallel or they are doing one by one. Matlab, first they are performing one by one convolution and they are performing three by three and they are performing one by one again. I mean, see, in Inception, normally what happens? The convolutions will happen in parallel.
Okay.
One by one.
Yeah, here also you can see.
That's what I'm saying. They are combining the results of, I mean, they're concatenating the results of the multiple convolutions. Or
yeah, you can see here. So it is 7 cross 64. So there are 64 such parallel feature maps. Yeah, have to.
So it is 7 cross 7 feature?
Yeah. So we have taken a feature map of 7 cross 7.
Okay.
Instead of 3 cross 3.
Normally it is always 3 cross 3.
Yeah, but you can also increase it or decrease it. So based on their experiments, they found out that 7 cross 7 initially has given a better performance. So it's like instead of keeping multiple 3 cross 3 and then getting a receptive field equivalent to 7 cross 7. So they've just taken a single 7 cross 7 field.
7 cross 7 cross 64.
64 is the number of feature maps.
Plus 2
Plus 2 is actually they add. Not adding exactly.
it's strike.
Yeah,
Strike.
strike.
Two strike equal to 2. It's not plus, it's S.
yes.
Yeah.
Yeah. So here they have kept on increasing the feature maps, and then here you can see they started to decrease it now. So first you increase the number of feature maps, then you decrease it, then again increase it, and then again you decrease it. It is something similar to other feature extractors. So now let's talk about the non-max suppression. So in non-max suppression, what we do is we try to sort our predictions based on the IOUs which you get, right? And after sorting it, we just ignore we keep a threshold. Okay, so based on the threshold, whichever is up, right, we just take that and compare the first one with respect to everyone. Let's say we take the top one and we just compare an IOU with respect to others, right? And then based on that, we just pick the topmost. So I'll show you on one Excel sheet which was there. Okay, so
So MTP is average precision.
what?
I mean,
Yeah, maximum average precision.
maximum average.
So Let me show you by that example. So let's say consider this as your input, right? And there are various predictions. Let's say so let's say these are my yellow and red are my anchor boxes, and black are my ground truth. Let's say that. Okay. So I'll be sorting it based on my box confidence score, which actually is basically my IU, right? So based on that, I'll be sorting all of them, right? So let's say this will be on the top, right? So this particular bounding box, since it's almost covering the entire village, and same way this particular box is almost covering the entire village, right? So we are going to compare this IU with respect to this. So we'll get a Jaccard index. So we'll just see whichever is above zero point 0.5, we will just reject them. So that what we mean to say is, so it's basically it's like talking about the same object. So when two things are talking about the same object, right? The IU will be high. Let's say these two bounding boxes are trying to predict the same thing, right? And so when I talk about IU, so the IU will be close to 1. So considering this as the maximum, I'm going to reject this bounding box. Right? Same way applies over here. So considering this as my actual one, I'm trying to suppress this bounding box, because these two things are talking about the same object, right? The IU will be close to 1 between these two predictions. So that's the concept. Any doubts? So here is my training. So you can see um, these are basically my parameters. So you can play around with that. So this is my learning rate scheduler. So I'm going to train in this particular way. So I'm going to reduce my learning rate by I'm going to keep it as 0.0001 initially, and then I'm going to increase it by 10, and again decrease it for another 80 pox by 5, I mean by 10, and then scale it up to 0.0001 for another, let's say when I cross 110. So the total number of epochs which I'm going to follow here is 160. Okay, so you can see that. And the batch size is I think for 32. You can play around with the batch size based on how much of compute you have. And, so I'll show you the predictions basically. Meanwhile, you can go. Yeah, so here I'm going to talk about how it increased the speed, considerably. When you saw 200 frames per second, right? How that happened. So if you see Darknet 19, right? So here, since you would have heard, right, BGG is a faster classifier than considering rest of all, right? So the Darknet 19 guys also followed the similar approach. Okay, so here also they use 3 cross 3 filters, and the number of channels would double at every step. After every convolution, the number of channels would double, and but here they're not doubling it as such. But then you can see over here. So this is the initial classifier, right? And then is 64, then is 128, right? So here they have doubled, and then they have again reduced it, and again they are doubling. So they're going to double it and reduce it, doubling and reducing it, right? And here they followed a global average cooling and a softmax for classification. So this is the typical darknet 19, which is kind of similar to the VGG 16 architecture.
In the code that you have shared, this darknet
Yeah.
classifier.
Yeah. So how they have trained for classification is, again, they have trained it for 160 epochs, right? And on the ImageNet classification, right? And and then they have trained for detection on Pascal VOC data, right? And that is again for 160 epochs, starting with 10 to the power minus 3 as a learning rate, and then after 60 epochs they are again divided by 10, so to minus 4, and after 90 epochs they're again doing that, so it will be 10 to the power minus 5. And they have used data augmentation while training the for localization, so not while classification, right? So it will increase the training speed, you can say. And yeah, so there is a concept of hierarchical classification which came out from WordNet. Okay, so that is, let's say, can everyone see the screen? Okay, so they're going to do a softmax on at this level. So let's say, so when you talk about WordNet tree, right? So I'll show you the tree example. So you can see, right, a bear and an American black bear, right? So when you combine cocoa and this, so there will be only a bear here in cocoa, right? But then in ImageNet there will be many more varieties. Okay, so they have treated them as the same for classification.
You clustered the same.
Yeah, they have basically, so during labeling, right? So they have played around with the labels of the ImageNet dataset to classify to help in the classification of the COCO dataset. So that's how they have combined the two classes. You understand by what I'm saying, right? Yeah. So that's how it's combined. And the same thing is done for all the objects as well. So if it is an animal, so let's say it's a dog, right? So again, there will be different breeds of dogs. So they have combined the labels of that as well as to be classified as a dog.
This is like, I mean, they want more data.
Yeah.
The underlying thing was that.
Yeah.
मतलब if there are independent classes in the data set, we can't, मतलब this technique won't help us. Suppose if I had custom data set and every class was independent of each other,
Okay.
so then I can't.
Yeah, you can't use that. So if it is a mutually exclusive set, then you can't do this. But if it is inclusive, then you can do this. So since there are different stages, right? One is classification, then is localization. So it depends on how you want to train it. But in localization, you cannot use that. So and let's again go through the paper. So this was the joint classification and detection which I was talking about. So if you go through this, you'll be able to understand this further. So I'll show you the results which I got. Let me just check. So I've created a new notebook. So suppose you have done your classification, right? So you can just download those weights, right? I mean, after training, you can just download your weights, right, on the notebook which I've shared, and then you can upload those weights over here, and run on that. So you can see the detection how it's going.
You have done a classification using darknet.
Yeah, classification and all those localization both by darknet, and then so I'll just show you the results now. So these are the results. So you can train it at home or collab or whatever you like. Right? So you can see these are the results. So it's detecting a person and a dog properly, and then it's detecting the chair and the clock, and you can see how it's detecting a person, right? And
This is the same code which are explained, right?
sorry,
This is the same code explained.
yeah. So, so you can see it's actually behaving well for streets and cars and all those things since the data set had much of these classes. Okay, so it worked well better for cars and street lights and all those things. You can see it's detecting every single car which you can see in this image. Right. So this data set is working well for that. Yeah, so it's detecting the train and police. Over here you can see it's detecting the giraffe and the zebra properly. But you can see there's a problem with the zebra over here. So it's saying that there is a giraffe as well. So it seems that my data set, had less of zebra and giraffe. So I maybe have to, improve on the classification, right? So these are the ways we can, randomly pick on and see like what's performing better and what's not performing, and then play around with that. So here it's detecting spoons and knives, and these are yeah. So that's all. So I'll be uploading this and the other notebook, so you can feel free to train it and test it out.
So this one you will upload, right? So the data has to be there on Google. This one, Drive. It has to be from there.
So I'm downloading the data from here. Show it to you.
Because with collab, you have to be familiar.
Yeah, one second. So I'm downloading the Pascal VOC data from their own server.
Is there a top?
What? Yeah. Actually, this mouse doesn't work with this thing. You asked about the data, right?
Yes.
So it's from this link.
Okay, look at.
Yeah, from this link, if you just do a wget, you can get download the data set.
And let us say that you have given this code link and run it directly as it is.
Okay.
How much time does it take to train?
It takes 2 weeks.
2 weeks to train.
Yeah.
Collab will.
Yeah, Colab will shut down. It just has a life expectancy of 12 hours. Okay, so you better need to save the weights in your drive. So you can mount the drive as well. I'll show you the code to mount the drive. Yeah. So using this, you can load your drive to your notebook. So using this piece of code, so you can mount your Google Drive, okay, and then create a Google Drive, My Drive, folder, and then there you can see all the contents of your drive. Okay, then you can just copy the trained model to your Google Drive. So basically, you are storing your whatever you're training, right? So that will be stored in your drive. Okay, it's after 12 hours or after every epoch, I'm actually storing all my training weights to my drive. Okay, and when you're rerunning it after let's say 12 hours, let's say the runtime gets disconnected, so you can again train it from the same position using this. So you have to again load them back to your drive, back to Collab, okay, and then you have to train it up. You understood, right? What I'm saying? So it's like you're just saving the weights after every 10 epochs or 5 epochs, so that you can load and save the weights. So, and how you can do that is over here. So I'm just checking my best loss. So based on my loss, I'm saving the weights as a checkpoint. So that's how you have to save it. So you have to check your validation loss. Okay, the validation loss has reduced considerably. Then you start you to save your weights and then load that to your drive. Okay, so mount your drive and then load that content to your drive. Okay, and then when you are retraining it, right, you can just load it back to your collab and then you can train it.
That will be a manual.
Yeah, you have to do that manually. So that's what. So I've done that. So see, I'm just pasting that, and below I've just pasted one more line, right? So wherein which does the opposite, takes from my drive and pastes it to my current collab, and then again I train it.
Basically, first you have had the weights in hand.
Yeah,
Now you are using the same weights.
yeah, I'm using the same weights to train it again. So that's a bit of manual effort which you have to do while training. And you have to monitor it basically because if you don't move your cursor or something, collab gets disconnected. So you have to just play around with collab. And there's a good news. So collab has increased its GPU size from 12 to now it is 16. So now it's on Tesla T1, I guess. So you can utilize collab better. So that's all for today's meetup, guys.
If you have more basic assignment where, for example, we are training the simple network and then doing transfer learning so that we can incorporate.
That's in phase one. So any transfer learning or basic classification if you want to do. So it's all the content is there in phase one.
I have to go through that. If you
Yeah.
can point out this one, just train a network, whatever network it is. Add one more class to it.
Yeah, so it's all there in phase one content.
Phase one.
So go around, get a touch into that. Go to GitLab and download all the content from phase one. If you want me to show it to you again. So you can access it from the meetup page. So here's the meetup page. Right. Over here on every session we provide the link to the GitLab account. Okay, so you can just click on this. And right now it redirects to phase two content. Okay, so copy this over here. Just go to phase one and go through all the sessions next time when you attend or something, and come back for the phase two. In phase one, we talk about basic classification, how to create your own data set if you want to start training from scratch on a new data set, and then how to do transfer learning. Let's say some data is trained on VGGNet, like on ImageNet, right? So you want to train on some new data set, you can just import the VGC architecture and then do a transfer learning or fine tuning, whatever, and then do it. And here we talk also about the style transfer, right? And audio style transfer as well as image style transfer. Then have a look on the session 6 content. So it has everything. Yeah. So that's what was session 6 about. Session 5 is about transfer learning and how to load your weights and stuff. Okay. And session 4 was about classification, I guess. Yeah, we talk about data augmentation techniques, which is on Yolo, right? So the same thing which you can see. We do a Kaggle class versus cats versus dogs as well, so you can do that and put your submission on Kaggle as such. And then in session 3 is MNIST, and we have actually created a web version of this, so you can uh, you can run the code. So over here you can write a letter, and it will predict it whether it's 2 or 3 or something. So it's basically MNIST classification. So how you deploy a production code, right? So that you can understand from this.
You have used some server to deploy.
Yeah,
Online.
yeah, yeah. Session 1 talks about basics. So that's all for today's meetup, guys. Thank you.